Hey everybody, we're on lecture 13 finally. See, I think we did 12 part 1 and part 2 and all of that. Lecture 13, primes and composites. And this is great stuff. Number theory deals heavily with this stuff, so you're really going to like it. And there's some classic proofs that we are going to master in this class. Proofs with far-reaching implications that are well within our grasp. So let's have at it. First definition, a natural number, p greater than or equal to 2, is prime exactly when it has exactly two distinct positive divisors, one in itself. And notice that these two positive divisors have to be distinct in order for the number to be prime. With that in mind, we might as well go to the remark that says, note that 1 is neither prime nor composite. Why? It only has one distinct positive divisor, and that's itself. So a prime number has to have two distinct positive divisors, exactly two distinct positive divisors. A natural number n greater than or equal to 2 is composite exactly when it is not prime. So what's another way of saying this? If a natural number greater than or equal to 2 is not prime, then we can't say it has exactly two distinct positive divisors, which means it has to have at least 3 positive divisors. So a natural number is composite exactly when it is not prime, and that means that a composite number has to have at least 3 distinct positive divisors. How's this? Less than 3 minutes into the lecture and I have to take a detour already. But it's an important one and one that we want to remember for the rest of our lives, and I'm serious about this. A preliminary observation to prove a proposition of the form P implies Q or R. First thing we do, we assume that P, the hypothesis, is true. Well, hey, if we're proving a proposition that has a hypothesis, yeah, first thing we do is we assume the hypothesis is true. And then we show that our conclusion, Q or R, is true. Assume the hypothesis is true, show the conclusion is true. Well, what's the big deal? Well, here's the big deal. The conclusion is a disjunction, an or statement. And this or statement can be true if Q is true and R is false. It can be true if Q is false and R is true. It can be true if both Q and R are true. The only time this thing is not true is when both Q and R are false. So to prove a proposition of this form, we assume the hypothesis is true, and we show that the conclusion, Q or R, is true by showing that both Q and R can't be false. We have to show that Q and R can't both be false. Well, how do we do this? Here's how. The standard method. Assume that one of them is false. Let's say Q is false. And then we show of necessity that the other one has to be true. So if we assume that one is false and show that the other has to be true, essentially we're proving that they can't both be false. And therefore, Q or R has to be true. And I mention this because this is probably something that, if we've even been told about this before, it may not have stuck. And I think back of my own experiences in grad school, and undergrad. Now, when I was a little boy back in the Stone Age, there was no such thing as a proof course in a math curriculum. Nowhere. And what would happen is we'd have 2 years of calculus and differential equations. And our instructors, if we were lucky, would sort of explain things in an intuitive way. Or they may not explain things at all. And they may have just said, look, this is an applied course, you don't have to understand it, just know how to do it. And so that's what we were fed for 2 years. For freshman and sophomore years as math major, we were taught to do calculus and differential equations. Well, don't worry why it's true, this is an applied course, just know how to do it. And then come junior year, all of a sudden we'd have courses that required skill in proving things like abstract algebra, number theory, analysis. And our instructors would do an about face and say, damn it, you've been math majors for more than 2 years now, you ought to know how to do a proof. And we'd look at each other and think, well, where did we ever learn how to do them? What, just instantly we're supposed to make the quantum leap from not knowing anything about doing a proof to knowing how to do proofs? It was an unreasonable expectation. And it was an unreasonable expectation that was imposed on all math majors back in the dark ages when I was a student. Now we do have a proof course. And we're exposed to this sort of thing, but it might not stick. And I'll tell you why this thing in particular is so important. As an undergrad math major and as a graduate student, we sort of learned how to do proofs on the fly. Eventually we got better at it. Eventually after that we got pretty good at it. But I can remember being in an abstract algebra class, and our instructor used to use this technique every so often. And I remember the first time he used it, he assumed the hypothesis was true, of course, and then he assumed that the first part of the disjunction was false, and he showed that the second part was true, and that was the end of the truth. That was the end of the proof. And the class ended, and I walked out bewildered, and I mentioned this to some of my classmates. Well, he showed that if Q is false, then R is true, but doesn't he have to turn around and now show that if R is false, Q has to be true? And they were just as bewildered as I was. Doctoral students, and none of us knew this. So this is something, even if we've seen it in our proof course, it may not have stuck. But the standard way of doing a proof of P implies Q or R, we assume the hypothesis is true, of course. And then we show that the conclusion has to be true by assuming that one of the two statements is false. Assume that one of the two statements of the disjunction is false, and show that the other has to be true. And in so doing, we're showing that they can't both be false. If we assume that one is false and show that the other has to be true, we're showing that they can't both be false. And if they're not both false, they have to be true. If both statements in a disjunction are not false, then it's automatically true. And this is the strategy that we're going to use in the proof that's coming up. It's exactly of this form. We're going to assume the hypothesis is true. And then we're going to take one of the statements of the disjunction and assume it's false and show that the other has to be true. And I just wanted to run this by you so that when you see it, you're not as bewildered as I was when I saw it in my graduate classes decades ago. Okay, here's the theorem. If P is prime and P divides AB, then either P divides A or P divides B. If P is prime and P divides the product of two numbers, either P divides the first or P divides the second. And here's our proof. And again, I hit the chicken switch right off the bat. I don't know how to do this initially, so I say, let the hypothesis be given. That is, suppose that P is prime and suppose that P does divide the product A and B. We've assumed the hypothesis. Now we're going to show that this disjunction is true by assuming that the first thing is false. And if this is false, P doesn't divide A, so P is not a divisor of A. But P only has two positive divisors, one in itself. So the only divisors that P and A could have in common are P and 1. And P doesn't divide A. So P is not a common divisor of both, which means the only divisor they have in common is 1. If P does not divide A, greatest common divisor of P and A is 1. That is, P and A are relatively prime. But that means, since P divides AB and P doesn't divide A, by Euclid's lemma, P has to divide B. And technically, our proof is done right here. But I just can't resist telling my audience what it was that we just accomplished. So essentially, I take this last line to tell my reader what it was that I just told them. What we've essentially done here is we've said P divides AB implies P divides A or P divides B, which is exactly what I proved. If this is true, then this is true. Well, did I really prove that? Yeah. Because I proved that this couldn't be false. The only way that this could have been false is if P didn't divide A and P didn't divide B. Oh, but we ended up showing that P did divide B. So P divides A and B, if P divides A times B, then either P divides A or P divides B. Now we're going to generalize this just a little bit. Okay, here's our next theorem, and I guess this is, I'm lying, it's actually a corollary, I think. We'll call it a theorem. If P is prime and P divides the product of n integers, then P has to divide at least one of them. If P divides the product of integers a1, a2, a3, to an, then P has to divide a sub I, where I is between 1 and n. P has to divide one of these guys. And it's an induction proof. And we want to do this because it's a fairly straightforward proof, and we want to have practice doing induction proofs. We started off the course doing induction proofs, and we don't want that to be the end of it. We learned how to do induction so that when it comes up in other things, we're ready, willing, and able to do it. Proof by induction. Show that our proposition is true for n equal 2. In other words, if P divides the product of two integers, then either P divides the first or P divides the second. or both? Well, isn't that exactly the statement of the theorem that we just proved? It sure is. So if p divides the product of two integers, either p divides the first or p divides the second. That's what our theorem that we just got done proving told us. Now we go to the induction step. Yay! Now the induction step. Assume our induction hypothesis. Assume that our proposition is true for n equals some natural number k, and show that our proposition has to be true for n equal k plus 1. In other words, assume that if p divides the product of k integers, then p divides one of those integers. That is, we're assuming if p divides the product of k integers, then p divides ai where I is between 1 and k. And we'll show that this means that p also divides the product of, we'll show that this means that if p divides the product of k plus 1 integers, then p divides one of those integers, some a sub I where I is between 1 and k plus 1. Let's see how we're going to do that. Okay, suppose that p divides the product of k plus 1 integers. Well, that's the same thing as saying that either p divides the product of the first k. It's the same thing as saying that p divides the product of the first k times the k plus first. But we can look at this product as the product of two integers. And by our previous theorem, that tells us that either p divides the first or p divides the second. And if p divides the first, then p divides a sub I for some I such that I is between 1 and k. Or, if this is true, p divides a sub k plus 1. Now what this means is, see, either this is true or this is true, which means that p divides a sub I for some I such that I is between 1 and k plus 1. So we've proved it. If p divides the product of n integers, then p divides one of them. P divides a sub I where I is between 1 and n. Or maybe I should say more correctly, p divides at least one of them.